In the last video, I put together some assembly code to get my math coprocessor working and tested. As part of that, I ran into an issue where when I'd go to read values from the math coprocessor on the data lines, I was reading all ones. And that was on maybe what I'll call the internal data bus at the processor side of things before the data transceivers. Being that I was running into some contention there between the math coprocessor and the data transceivers that would have been pulling in from the external bus into the internal bus at the same time, I had shifted my data connections for the math coprocessor to the external data bus. And on this visual on the screen to the right, that's how I've indicated I'm using the external data bus as bus underscore, and let's say D15, D14, etc. And that worked, and so that was a workaround for the problem I ran into. Feedback I've received since then, posting on the YouTube video, is that, well, ideally you'd actually keep that coprocessor on the internal bus. And so I thought, okay, if that is the case, then this should be workable. So I've just got to figure out what to do to make it workable. And essentially my goal is then to turn around and bring the connection back to the internal data bus, in other words, right off of the processor instead of off of my bus board in the center of the system after the data transceivers. Well, that got me curious then, so I jumped out and I looked again at this. This is from the 287 data sheet from Intel. And the part I have highlighted is what's probably most important here. So down below is my 8287. And so with this 287, one of the lines that I need to work with is this, basically an enable line. There's two of them. There's one that has to be pulled up and one that has to be pulled down simultaneously. So I've done, like this diagram shows, I've actually pulled my NPS2 high. So that's just always high, tied to VCC. And then NPS1 I've been using, and I've got my own logic in my PSOC that controls that, basically just based off of address decode. And that worked fine for that. And then the transceivers then have an output enable, and I've been controlling those with the DEN signal off of my bus controller. And again, that's worked when I have my 287 on my external bus, in other words, to the right over here. But when I had it to the left of the data transceivers is when I ran into the issue. Well, as I've studied this graphic a little bit more, what I've noticed is a few things. Let me first start by saying this is how I have it connected, or had it connected, I should say, in the last video. But that's kind of a simple approach. It's incomplete, quite honestly. So what I need to look at is there's this NAND gate, and what they're doing in this schematic is, before we get to that output enable, we're going through a NAND gate. And what's feeding that NAND gate is DEN. That's one thing. I've been running DEN through an inverter and bringing in an inverted DEN into my active low output enable, and that's as simple as mine has been. This is taking DEN, not inverted, into a NAND gate, along with some output of this logic here. And there's a 74AS138, and then there is a latch here. And in a video way back when I was talking about the math coprocessor, I kind of just manually decoded or converted what I saw here for logic into what address I was going to put my math coprocessor on. And at the time, I wasn't even sure that I had to use that address. I just chose it because that's what this showed. And it looks like actually that address, you do exactly have to use the addresses that they're using here for the math coprocessor. And so in my PSOC, I'm doing address decode. But there's other things in this 74-138 that they're taking a look at that I'm not. And two of those things would be the IO, so MIO, and int A. And this is the COD int A off of the processor, not the int A coming off of the bus controller. And then we've got the address up to the right. So the upper right part, all of that, I'm doing that something comparable in my PSOC for address decoding, but I was not taking into account MIO or int A. And so what I did is I recently updated my PSOC And I brought in two new signals into the PSOC, so my MIO signal and the COD int A signal. And then I updated the logic so that for my math coprocessor enable signal that's going out, I'm looking at A7 down to A3, plus I'm looking at this net IO, which is basically an inverted MIO. So that means that if IO is low, it's an active low, I'm going to invert it to high and send it into the NAND. So I'm going to filter down and make sure that I am doing an IO type of address space for this math coprocessor to be enabled. And then underneath that, I'm also going to then look at COD int A, and that's got to be high. And that's telling me that it's not doing an interrupt, basically. So if int A went low, I'm in the middle of an interrupt. So this is going to say only let the math coprocessor work if we're not in the middle of an interrupt. That's at least how I'm interpreting all of this as I go through it. So I updated the PSOC. My math coprocessor enable, I think, is closer now in its intention of the author of this schematic to the left. So I'm now taking into account those extra two signals, MIO and int A. I'm using DEN, and you'll see here where I'm using DEN in just a second. But all of this I'm now taking into account much closer to what I see in the schematic. So I added a NAND gate to my system, and I'm going to bring DEN in. I'm also going to bring in my math coprocessor enable signal, first running it through a latch. They're showing a latch here, and this enable signal, they're coming in right here and they're latching it, and I'm doing the same. So I come out of my PSOC into a latch and then into this pin. And I want both of these to be high, so I want it to be an active high DEN. And then I also want to have the math coprocessor enabled to be high, meaning I'm not doing math coprocessor work, for this output enable to be active low. And that's what I'm going to send over to my data transceivers. So if the math coprocessor is working, if this is basically active, if it's low, that means that this output is going to go high, which means I'm going to turn off my transceivers and I'm not going to pull in that contention that I was running into before. And so with those, I then come in here and I update my data transceivers. I bring that data OE line in for the output enable. And then I went back to not using the bus, external bus data lines, and instead using that internal close to the processor before the data transceivers for my math coprocessor. And this is what it looks like, and I've gone ahead and done those changes and everything is working at this point. So you can see my PSOC's getting a little bit messier. I got more stuff flowing in and out of it. I brought these lines out for my data, so straight from the processor into my math coprocessor. When I first wired this up, remember I had run lines here, and then I ripped all that out, and I then moved them off of the bus over here. Well, now I've ripped that out, and when I came back to this, I redid it. I went with these soldered PCBs again that I could click in, because I noticed even on that last time I did this right here, some of these wires were trying to creep out from the get-go. So I did this little solder board, and again, it's a much better connection. So that's in there, and that's coming down here to my math coprocessor. So all of that's done. Output is tested and working just fine. So I think I'm good to go there. And just maybe a slightly zoomed in picture if you want to see that better, but it's probably hard to decipher anything here as far as wires, other than I have my data lines coming down. I've added some more control lines going in and out of this PSOC to support everything I'm doing. Now, as far as the two address lines that come to the math coprocessor, I am still using those off of my latch over here, and that does match what I see back in this schematic here. So they're bringing in A2 and A1, and they're latching those. So I'm just using the latched version of A1 and A2 to match what I'm seeing here. I did try using A1 and A2 unlatched, in other words before the latches, and it would not work. And I didn't dig into it any further. I just tested it. It would not work, but it works fine out of the latches. So I'm going to stick with the latched version of A1, A2. this is all good, and seems like this is maybe more of the intended way to set this up. I'm sure you can do this 100 different ways, but that's how I'm doing it now. Now, one consequence to this, I believe, is that backing up here, my Arduino up here is only tapped into the external data bus. So if I'm going to be doing data transfers between my processor and the coprocessor, I'm not going to have visibility to that data from this Arduino. And that's come in handy in the past. So when I was troubleshooting my 287, I was looking at those data values on this, basically whatever bus the 287, at that point it was the external bus, but I was looking at that to help troubleshoot. So I still think I want to be able to get visibility to the internal data bus here. Got a problem though. If I look at my Arduino up here, I don't have much left for connections. These up here in the upper right are things like powers and grounds, resets, whatever. There's no I/O pins there for me to use. These I/O pins here I can't really use because they're used for the USB communication, if I'm not mistaken. So then I have a handful of connections here, maybe 8 if I'm counting that right, that I could use. But I want to get 16 more data lines run up to my Arduino, because what I would like to do is be able to show data on the external bus and internal bus, and maybe even put in logic so that if I am doing a math coprocessor type of thing, I show the internal data bus, and if I'm doing other types of things, I show the external data bus. And now I'll need an indicator to show, am I showing the internal or external data bus when I show the data values. So how am I going to get away with this few pins? I don't want to add another Arduino. So I think what I'm going to at least take a run at, I think in theory this should work, is I'm going to use a pair of 74 165s. The only ones I have on hand are the old 74 165s, not even HC, not LS, none of that, just 74 165. And then I have just 2 on hand of the 74 LS 165. So I think I'm going to use those 74 LS 165s for now. I'll get some HCs or other flavors ordered up. And I think if I have this right, I can get away with only 4 pins that I'm going to use out of this bank down here. So up to this point, all of these I have used. Coming over here, I've got these reserved for the USB serial communication. All of this is used all the way up to the ground. Maybe I have 1 free in there. I'd have to go double check, but there's not 16 free. But what these 165s should let me do is read 8 signals here and submit it as serial data up to the Arduino, and then read the other here and serial data up to here, which means I'm going to have to send a clock out. So one of these pins up here I'm going to use as a clock out. I'll go to both of these chips simultaneously. There's another one, another signal I'm going to have to send out that basically I'll use to say load the values off of the address or the data bus, and then another one that when I flip the value of that lets me then start reading the serial output of that. So I'll read in 8 bits, read it back in serial, read out parallel 8, read it in serial, and I should be able to do those simultaneously. So I've got a pair of serial lines that'll come up, one from each of these chips. So I'll have a common clock that'll go to both. I'll have a common SH load, so kind of the serial or parallel load. That'll be common between these two, and then they'll each have their own unique serial. So one for the most significant byte, one for the least significant byte. So 4 lines up to the Arduino, I think, will get me all of this. It also means that for every clock tick where I'm going to go read data from my normal external data bus, inside of that I'm going to have to do 8, I don't know if you want to call them subclocks, or basically 8 ticks within that single clock to bring in all the serial data. I don't know if that's going to impact the performance of this debugger or not. I think most of the bottleneck is the serial data that I'm trying to send to the PC. It's not I don't think the Arduino itself and reading the values on these pins is the bottleneck. So I'm going to give it a shot and see if I can read these 16 data lines through just these 4 lines and still show it in my logged output without impacting performance of what gets sent to the PC, to the Windows application to view it. We'll see how it goes. I'll just experiment. This just sounds like something fun to do. So I'm going to bring that up into this header here, and like I was saying before, I'll take 8 lines to each of these 165s, and then I'll take 4 lines and run that around the board. I suppose I'll probably wrap around the left side of this since it's already kind of messy, and plug in those 4 lines up here and see if I can get that debugger to work and show me the internal data bus in addition to the external data bus. So I want to provide an update. Thank you for those that submit comments, like in this case the comment about I should be using ideally the internal data bus. A little bit of rewiring, and that seems to be working just fine.